Good morning, esteemed colleagues in Cathodic protection. Today, I want to briefly and concisely talk to you about a coating quality inspection technique, which is called DCVG, known as direct voltage gradients. This time I'm going to do an inspection on a buried cable where I'm going to create 3 faults. This is one of the faults that I'm creating right now, like a lateral cut, where we can see, there it is, on the right side of the screen. Let's see if we can see the cable and observe the details of the cable clearly visible in the image. There is the fault, but it's a lateral cut where the insulation is still intact over it. I'm going to cover it up. When I bury it, it's going to be covered like this. This is a fairly common fault. When the cables are being installed, they are being pulled through pipes, and there are sharp edges that damage the protective coating of the cables. I'm creating a second fault, but this time it's a B cut where the cable is visible. So I want to see how the behavior of the voltage gradient signal is when the material is like this. There is indeed a third fault, which is specifically like this. Total exposure of the material, where I also want to see, in particular, the behavior of the gradient with this type of fault, and as well. So I'm going to proceed to explain how to install the equipment of the switch, of the portable rectifier, the temporary setup that I'm going to improvise to see how the behavior will be of the faults in this cable. From the coating perspective, I'm going to place some stakes indicating where the faults are so that I have that reference. And I'm going to have some final stakes for the initial signal and the final signal. This is going to be my final signal. And the initial signal for me is going to be, this one is, so from here I would start my inspection up to the final signal, which is next to the wooden pole, the alternating current supply pole. I continue with the preparations to teach how to apply the DCVG technique and how to use the equipment. Good morning, dear colleagues. Bravo.
Pizza table. Show it on the screen and the defect of the retained cable where I created 3 faults. A vertical cut that was behaving with a small defect. I made a second cut where I'm simulating a moderately sized defect in this particular experiment, which is being conducted. That is a cut in B where the surface of the slope can be seen. I made a third cut where I caused a severe fault, that is a circular cut where it was exposed, like half an inch of the cable area that is in red. The purpose of this explanation is that the CD technique also helps us detect faults in buried cables once they have been installed. And it can also tell us precisely where we will be able to make the specific repairs in any case if necessary. However, to establish and support this test, we need to install a temporary cathodic protection system. For that, we are going to resort to, from a portable power plant, which is going to be our power source, we are going to use a portable rectifier, AC-DC converter, as you can see, has coarse adjustments, fine adjustments. It has a subdecimeter, perimeter, and protection brakes, which are its positive output and negative output. We're going to place the positive on this bar. This is going to be my temporary anode, right? There may be several bars in a sugarcane bed. In this case, I need just one because I don't require that much energy to reach the cable since it will go beyond the range of the presentation. What gradients can I measure? Basically, this becomes my anode. The negative cable, this spool of cable I have here, has a cable that goes all the way over there where I have the stakes. The buried negative cable. That becomes my cable that I want to evaluate. Or it could be a pipe You can extrapolate the two functions. What I want you to see with this test, with this trial, is how the gradients behave based on these. From this current injection that I'm going to do, I'm going to generate some gradients. And to generate this type of gradients, I need to inject an asynchronous signal. How do I achieve this? Through a programmable switch that already has its interruption frequencies. Here we have the suitcase where we have the DSB equipment. What does it consist of? The equipment has a programmable switch. Let's go. Some interruption cycles from 1 to 5, where in the back I can see what cycles it has. In position 1, it will be 0.45 seconds on and 0.8 seconds off. It indicates to me that this is for doing CVG, or I can select from 2 to 3. But in this case, I'm going to select cycle number 1. It has a connector for the satellite antenna. It has an indicator for the satellite antenna. Normally, we have this type of antenna. We connect it. It has a precise fit, and we secure it. Now we have our satellite antenna connected. When I activate the interruption switch, I have an indicator LED that will show me if it's activating. Indeed, that LED activates. And on the back here, I have a green LED, which is indicating that it has a satellite signal. So it's capturing the satellite signal. Normally, this equipment is connected in series just with the switch. The negative from the rectifier, which is this wire, goes to the negative terminal of the switch. And the other end, which goes to the cable, is where I'm going to make the connection for structure, the pipe, or the cable that I want to evaluate. Let's remember that the positive will always go to the bar, to our makeshift terminal. What else? What other equipment makes up the DCVG? We have the measuring equipment, we have the controls, or the control knobs, which connect to the measuring rods. Inside its case, we have some rods that already have their copper liquid, their copper solution. They have a porous wooden tip, this porous tip, along with these tips that we can see here. Here we have some spares, and the idea is that they are always saturated with the electrolyte so that they make contact with the ground. I'm going to assemble one of the rods. It has its threaded fitting.
When you turn it, make sure not to apply too much pressure, as this could cause issues. The goal is to ensure it remains stable and secure. I will return shortly with the other baton, which is currently halfway through the process. This step is crucial to ensure everything is aligned and functioning as expected. It's important to handle each component with care to avoid any potential mishaps. The stability of the setup is paramount, and I will ensure that all elements are in place before proceeding further. Please be patient as I complete this task. We adjust it without overdoing it, and now we have our baton assembled. This equipment consists of a harness and a backpack to install the satellite antenna so that the equipment can capture that type of data. This is the satellite antenna, portable for the measurement equipment. We simply attach it to that backpack. And now we have it assembled. This connector, which is specifically designed and engineered for this particular type of equipment, has its fitting conveniently located on one of its sides. We simply present this side connector to the equipment and make the necessary adjustment to ensure a perfect and secure fit, allowing for optimal performance and functionality. We already have it connected with its antenna. He brings two connection cables, one for each control. The control where I can adjust the dial, which is this knob and this impedance adjustment. It has its very characteristic connector, which is this type, where we couple it, tighten it, and we also check the knob to make sure it makes good contact. Let's ensure this. because it can lead to a lot of errors. Make sure to have a good contact. Let's make sure of this, because it can lead to a lot of errors. The other control, which is quite different from the first one, doesn't have a control knob, just a banana connector that we present here, and we already have it ready all the time for your convenience and ease of use. This setup ensures that you can always rely on it being available whenever you need it, providing a seamless experience. This control is for the right hand, and it has its specific fitting for the right side. If I present it, it fits, and if I want to take it out, I press this knob, this button, and I pull it out. However, if I try to place it here, it doesn't fit. That is to say, its fitting is specific for the right side, to manipulate it with the right hand. The other one also has its specific fitting for the left side. I already have the CVG equipment assembled. Now I'm going to proceed to take measurements. I'm going to activate the temporary system and proceed to take the measurements to ensure everything is functioning correctly and gather all necessary data for analysis. And at this moment, I have voltage in the circuit as it is crucial for the experiment. I want to check if the switch is working for me and confirm the system's reliability to ensure the system is operating as expected. It's causing the interruption. In this case, I'm going to install this portable resistor with a bulb, and I can see that it's interrupting. I resort to that because I can also do it with a multimeter on a perimeter piece, but since they are very small currents with very low density, I need to check if it's really interrupting, and here I'm checking it. I already know that the system is operational. It's injecting a voltage, and it's causing the interruption. I'm going with the telegenre order equipment to the area where I need to do the test. Okay. Normally, we connect the baton to the right hand and the baton that doesn't have dialogue or control to the left hand. Notice that when it's active, I have a blue LED, indicating that I have a satellite signal. And the status of the LED is green, which means the system is operational. It's giving a low battery alarm, but I hope we can do the test. I'm going to set it to the 10-volt scale right now. To check if I have an input signal on the cable I'm going to evaluate, I make physical contact with one end of the stick, and here on the dial, notice that when it's on number 6, it makes this specific movement. In order to properly and accurately check, I carefully and thoroughly make sure that, as you can see, right here on this dial, specifically, exactly at this point in time, it makes this specific movement. That means the current is coming in here and going out there. That means it's coming from this stick, coming from the ground, and it's entering where I'm making contact. That's what this equipment is indicating to me right now. That's the direction of the current. I have a signal. Right now I have it at 10 volts. I practically have almost 4 volts of input signal. These are some of the requirements needed to perform SVG. In the initial signal, we should have a minimum of 1.5 volt, maximum near the drainage point. Excuse me for that mistake. For me, this becomes the drainage point because it's the closest point of the makeshift or temporary setup that I'm installing. It becomes my drainage point. Drainage point in this case must be a signal. At least 1500 millivolts or 1.5 volts, the final signal, which is over there where the wooden touch is. The other orange flag should reach at least 150 millivolts over there. If it's below 150 millivolts, I shouldn't start the test. What do I need to resort to? Increase the voltage over there in the rectifier so that the final signal reaches 150 millivolts. If there are a lot of damages in the coating, there will be attenuation of that signal. If I start here with 1500 and over there it's below 100, for example, it means that there's a lot of coating, the resistivity of the ground. The quality of the coating also influences it, like chloride, pH, temperature, and it's going to attenuate the signal. Another essential requirement for doing CVG is that the ends must be insulated. In this case, the tip is in the air, and the other end at the end is also in the air. That is to say, they are insulated. The same principle applies to buried pipes.
that broke off from the oil. Another condition for doing the DCG test, aside from the signal, the insulations, I'm talking about joints, insulating packers, monolithic joints, the magnitude of that signal. As I mentioned, 1500 and 150 at the end. Now, I have already measured my input signal here. There's a protocol for starting the inspection. That is to say, I have to measure here. I check. The whole signal, it comes out to about 4 volts after that. With this extension, with this cable, at a distance of 15 meters. I place my central point here. I use one of the rods as the center. And this other rod connects with this extension cable. And another person would stand over there to measure the remote gradient potential. After I do that, this equipment has the ability to record the type of data I'm capturing in the field. And then I have to take the measurement, step by step, to measure that remote gradient. How is it done? I position myself at the center. I open up a space of about 2 meters. I place the device in a position where it can capture that reading. Every time I lower the reading on the equipment, I'm adjusting the dial here to center the needle. I have to turn this knob to reduce the sensitivity. I change the impedances. Here it's indicating that I have 1. When I have it on the 25 scale, it essentially means that from 0 to here is basically worth 25. If I set it to the 100 scale, I practically have a deflection of almost 1 division. It would be about 2 millivolts. I open it again. If I get the same measurement again, I consider it as the remote gradient of that measurement point. Now I'm going to track a casing failure. How do I use this equipment to locate it? I start from the beginning, always keeping a distance of 1 or 2 meters. I set it to the lowest scale. In this case, it would be 10 millivolts to give it the highest sensitivity. I'm trying to adjust the dial to see if I have any defect that's calling my attention. It's very sensitive there. But well, let's see if I can reduce the sensitivity a bit more with the potentiometer. Let's increase it. I have a small indication. When the needle is here in the center and makes this bend, it tells me that the current comes in here and goes out over there. It comes out this way. So that means I have to keep moving forward. To move forward, notice where I have the stick. To move forward, I place the next stick